All right, so tonight we're going to cover some topics that kind of extend linear regression, kind of give you more tools to work with and more things to think about. So start off, here's your outcomes for this evening. First is to understand the bias variance trade-off. You're also going to learn some techniques to prevent overfitting and deal with that trade-off. You're also going to learn to utilize ridge and lasso regression and also understand using AIC and BIC. So tonight's going to be all about kind of better fitting models and setting them up to make predictions on unseen data in the future. So to start off, we're just going to import some stuff here. If you notice the second line, this is something that I just kind of figured out. So NumPy will do like scientific notation if it's too like small or large of a number. You can actually suppress that if you don't want to deal with the scientific notation using this. So just something to keep in mind. All right, so to start off, we're just going to generate some random data and I'll plot it here. So this would be our data. We want to plot a regression line for this. You can notice there's an obvious curve to it. So doing just normal linear regression, just plotting the single feature x, we get this model here. You can see that R² is very low. We can take a look then at how this would look if we plot that regression line. And you can see since our data is curved, it's not linear, just a single linear regression will not accurately fit our data here. So we need to add a quadratic term since this has kind of a U shape. So we're going to create a quadratic term basically by squaring each of the values in our x, our one feature. Then we're going to use numpy.stack to kind of combine the two. So we'll have a column of just x's and then a column of x². And then we're just going to pass that into an OLS. And you can see now we got a much better R² at 0.9. And if we go ahead and plot this, you can see it fits our data much better. So sometimes we have to basically add features to our data in order to develop a model that accurately fits the data. And this can go on past quadratic, it can go any order of polynomial. So this is known as polynomial regression. So I'm going to generate some more random data here. You can see this has a bit of a different shape. It has a couple different curves. So this one might need a couple different polynomial terms. So this function here will just take in, this is for one single feature. It won't work if you have more than one, but it'll take one feature, the order you want to go up to, and it will return data that has each of these polynomial terms added. So I think I'll have an example here. So if we pass in 3, this should do x, x², and x³. And that's what these 3 columns represents. So we could start off using our order of 3. And we're actually not going to use sklearn for right now, and I'll explain why later. So just ignore that. We're going to stay with stats models. So fitting with the cubic term added, we have 0.79 for the R². So it seems to be a decent fit. We can go ahead and plot that here. You can see it kind of lines up, but it's not really addressing like this curve here, for example. So we might need a bit of a higher order. But so the question becomes, what order do we need? At what point do we stop? So this loop here will go from 1 to 21, and it will add that number of polynomial terms each time. And then we're just going to keep track of the R² and the mean squared error to get a sense of how well it's fitting to our data. So we'll run that loop. And now we're just going to plot out the R² and the mean squared errors, how they changed. So from this, you can see kind of a trend here. As the order goes up, the R² gets higher. As the order goes up, the mean squared error gets lower. So based on this, does someone have a guess of what order we should choose? Anyone? Juliet, what do you think? If you had to guess. just from these two graphs? What order do you think would be best?
The second one? I don't know. The
Second order?
yeah. Oh,
Even though like order 20 has the highest R squared?
right. My bad. 20,
Okay.
I would think.
So if you think 20, we'll go ahead and plot all of these out here. So for each of the orders, we're going to plot the regression line and see how it lines up with the data. So as you see, we add an order each time. It fits more and more closely to our data. But you can see it starts to do some wonky stuff with all these kinks in it here as we get higher and higher. And at the final order 20, we can see it goes through all the points, which we might initially think is good, but we'd be wrong. So now we're going to generate some new data using the same formula as the original data, and then run our model on this new data and see how it performs. So in the blue is the true value of our new data, and in the orange is what we predicted using our model. So you can see we're kind of all over the place. We did not handle this new data very well at all. So this is what's known as overfitting. So basically, the ideal situation is you don't account for every single point and end up with a line that has a bunch of kinks and curves in it like this. You want to have more of a generalized fit so that when you add more data, it's better suited to predict those values. So you could tell probably from the equation I used to generate that random data that we had up to 4 polynomial terms. And you could also tell by the number of basically hills and valleys. So like, might remember from math class, like a quadratic has 1 curve, a cubic is going to have 2, so on and so forth. So you can kind of count how many curves, maximum and minimum you have, and that will tell you what order you might need. So we know here it's 4, so now we're going to fit a model with 4 and then run predictions on that same new data. And you can see that it fits the new data much better. We have a lower mean squared error. So there we saw that we overfitted. We only needed 4 polynomial terms, even though adding more polynomial terms initially increased the R squared and lowered the mean squared error for the initial data. But we can see how that didn't really apply then to the new data we added. So this kind of plays into the bias variance trade-off. So you'll see this graphic a lot. It's because it's probably the best one at representing this. So you can see cases with low variance, high variance, and then low bias, high bias. So in our example we just did, we had probably low bias, or no, wait, we had, let's see. Yeah, we had low bias, but we had high variance. So we ended up overfitting.
Can you explain bias and variance?
Sure. So bias basically means that we're not accounting for everything in the data. We're not explaining it well. So you can see when we go from, if we have low bias, basically you want low bias. If you have low bias, then you're close to the accurate true prediction. If you have high bias, you're kind of off. You don't have all the data you need to explain what's going on. Variance is what happens when you overfit. So basically the model tries to account for all the random noise and stuff in the data. And it can end up like this, kind of spread out. It won't fit well to the new data. So you want a model that has both low bias and low variance. So in other words, you want a model that is complex enough that you can explain most of the data, but isn't too complex that it makes the regression line all curvy like that and tries to fit to every single little point. You want kind of like a generalized regression line that explains what's going on in the data and will be able to accommodate new data as you add it. Does that kind of answer, Bonnie?
Mm-hmm. Thanks.
Okay. Yep. All right, so we need to find ways to prevent overfitting then. In the case we just saw, we knew from the equation and from the graph that we needed 4 polynomial terms. It's not always going to be that easy. We're not always going to have just one feature. So there's lots of things you can do to prevent overfitting. You can do a train test split, which you guys may have had some experience with, where you basically set aside a portion of your data. You don't build a model on that or anything. You only build a model on the training data. Then you can use the test data the model hasn't seen to kind of test out how it would perform in the real world with new data. And that lets you kind of compare models. Another method is cross-validation, which is basically doing a train test split, but kind of multiple times in a row. So it keeps cutting up your data in different ways, getting different subsets of it, and running the model on each of those, and then kind of averaging and summarizing results. And then the next two we're going to, or the next three things we're going to use here tonight are adjusted R-squared, AIC, and BIC. Adjusted R-squared, you've probably seen, it's pretty much like R-squared, except it gets penalized if you have a bunch of features. So if we added those 21 polynomial terms, our adjusted R-squared went down probably. I'm trying to, might be able to see that here. So if we do this and then do model.summary. So I mean, in this case, it's just a little bit lower than R-squared, but generally if you add like a lot of features, it will really tank the adjusted R-squared. So in addition to adjusted R-squared then, there's AIC and BIC, which we will get to in a second. I'm first going to make another data set. This is going to have 100 rows, 10 features, and we're going to try and do a couple different things to develop a model for it. So the first, we're going to do that train test split. So you import it from sklearn model selection. You'll use this a lot. You'll just have it memorized here once you've done it a few times. You basically set it up like this. You do xtrain, xtest, ytrain, ytest, and then you're going to pass in your x and then your y. And then your test size is what proportion of your data you want in your test set. It's kind of arbitrary what you choose. Typically, it's like 0.15 to 0.25. Usually like 0.2 is an average value. Kind of just depends on how much total data you have. And then random states here just so that this always picks the same split of training and test data. So we'll go ahead and run that. And now we're just going to build a base model, just fitting to the data as it is, all the features. And then we're going to calculate the mean squared error on the test data and the training data and print those out here. So you can see here's the training, mean squared error, and then the test. So this gives us like a baseline. So now anything we do, any other models we try out, we want to try to beat this basically. So the first thing we're going to do, so besides adding polynomial terms, you can also add interaction terms. So interaction terms are basically if you have two features and you multiply them together. So sometimes it's not just a feature by itself that impacts a model, but when it's combined with another feature having a high value, that interaction can be more significant towards explaining your final target value. So I know this says polynomial features here, but a neat trick of it is that you can get interactions only from it. And so what this will do is generate interaction terms for everything in our data set. So try to explain what's going on here. So we had 8 features. So we had x1 through x8. So these first 8, so 1, 2, 3, 4, 5, 6, 7, 8. So those are just x1 through x8. So then starting here, this would be x1 times x2, and then x1 times x3, so on and so forth, basically all the permutations until the last one would be like x7 times x8. So it gives us all the possible interactions that could happen between all of our features. So as you can imagine, this would probably lead us to overfitting because it's just a ton of features. There's probably not that many interactions there. So let's see here.
Hey, Matt, here,
Yeah.
why you create the features for train dataset and also for the test dataset?
Because we want to run our model on both the train and the test set, and like they're separated out right now into two different arrays. So we have to generate the interactions for both of them in an equal way.
Oh, okay.
Yep. So I'm trying to run this down here and it's getting cut off. There we go. Okay, so this is a model that's fit with all of our interaction terms, so all like 50 of them or whatever it is. And so we can see our mean squared error for the train went down. So before it was like 4 something, I think, and now it's 2, so that's good. But our test mean squared error went way up. So what this clearly tells us is that we're overfitting. We're fitting really well to our training data, but too well so that we aren't doing well on the test data. So there's more we can do because we have a low training error, but we're clearly overfitted. So now this is where we can use AIC and BIC. So there's a lot of math involved in how these work, calculating them. It's kind of outside the scope of tonight, but I do have some resources for you if you'd like to get into more of the details of how it all works. But basically, they're two metrics. You already get them in your OLS results table. You've probably seen them and wondered what they were. They're basically metrics that seek to do what we've been doing tonight, maximizing our model accuracy, but minimizing its complexity. So trying to prevent overfitting. So they basically tell how good your model is at representing the true reality of the data. So they basically assume that your data is like a small sample of the total population, and it kind of uses some statistics to make assumptions about what the true population might be. And it kind of tells you how close of a fit it's likely that your coefficients are to the true nature of the data. And they're basically used to compare model performance. So we can try out a bunch of different models. Maybe some have these features, some have these other features, and we can use AIC and BIC to compare them. And the thing with both of these is that lower values are better. So you want the model with the lowest AIC and BIC. So you're probably wondering, well, like, what do I choose? What's the difference between the two? Generally, both are important. You kind of want to consider both. There's a lot of different viewpoints and arguments on like when to use one over the other. There's a lot of math involved in trying to figure out what they each actually mean about your data and depending on your data set. But in general, this is kind of like a way to think about when one might be better than the other. So AIC might be better when you don't know what the true model is. So you don't know like what your data is representing, what the true population might be, and you don't think it's one of the models that you're testing out. BIC might be better when you do think that you have one of the true models that you're testing out and you're trying to figure out which one it is. So that's kind of one difference between them, but really you'll use both. And you kind of just have to see if a model has, significantly lower AIC, but maybe slightly higher BIC, then that's probably the better model. All right, so here we're going to take basically all of our data. We're going to generate all the interactions again. And now we're just going to see what we get for our adjusted R-squared, our AIC, and our BIC. So here we have a decent adjusted R-squared. And the thing about AIC and BIC is that you can't just look at this and know how good it is. It only matters in relation to other models and other AIC and BIC using the same data. So we kind of just have to store this. This is kind of like our baseline now that we're comparing stuff to. So a way to figure out which of our features to keep in is called recursive feature elimination. You probably use something similar in the first project with like the stepwise regression where you kind of go through and, add a feature each time. In this case, you remove one each time. So you remove the worst one. So you basically import it from sklearn. you have to pass in a value here that tells how many features you want. And then step is just how many to remove each time. So in this case, we're just going to remove 1. So what this does here is it goes through from 1 to the total number of features we have, and it will run this recursive feature elimination to find the best features for that given number. Then we're basically going to build a model using just those features. And then we're going to keep track of the AIC, BIC, and adjusted R-squared so that we can compare them all and hopefully decide how many features and which features are best for our final model. So we'll go ahead and run that. And now we can look at the adjusted R-squared. So hopefully you can see this. It's kind of tiny, but on the x-axis is the number of features. And then this is adjusted R-squared. So you can see it kind of increases, plateaus off, and then kind of starts to decrease as you get more and more features. So from this alone, you know, you'd probably want something between like 15 to, I don't know, 40, somewhere where it's highest here, where it's level. But we can also combine that knowledge with the plots of AIC and BIC. So this gives us kind of a more pinpointed location of where the number of features might be best. So in the, let's see, in the red is AIC and in the blue is BIC. So you can see they have kind of different shapes. They have different minimums here. But if I were to pick a point, I'd probably pick their intersection here because that's the point where they're both collectively the lowest. So that looks to be 19. So for 19 features, that might be the best if we're trying to minimize AIC and BIC. So now we can choose those 19 features again with our recursive features elimination, and then basically build a model and then look at that R-squared adjusted and AIC and BIC. So there we have 0.82, which was better than our baseline on the adjusted R-squared, and both the AIC and BIC are lower. So that's a better model. So now another method we can do is what's known as ridge and lasso regression. So they're basically different versions of linear regression. They just have a penalized term added. So they're known as regularization techniques, and they basically do all the stuff we've been talking about, trying to control the model complexity and to prevent overfitting. So I'm going to throw an equation or two at you here. I'll try to explain it. So this part here, well, first of all, this is just the loss function. So you have to kind of think back to the gradient descent we were doing. So ignore everything to the right of this. So this was just our normal loss function. You know, we're trying to minimize the squared differences between the true and the predicted values. But now we're adding this term here. So this is lambda. This is just a parameter. It can be like anything from 0 to infinity. It's basically the weight, basically how much this penalty term matters. And it's something that we adjust and we try out. So the beta here is the, it's basically the sum of the coefficients. So if we have our equation here, 5x1 plus 2x3, it would basically be 5 plus 2, that's 7, and it would be, or each one squared, so it would be 25 plus 4, and so it would be 29. So adding that term there to our loss function basically tries to make the model minimize the coefficients for each of our features. So that will kind of reduce the complexity of our model and make it more generalized. So lasso regression is pretty similar, but a little bit different. You'll notice at the end here, it's almost the same, except it's just the absolute value of the of all the coefficients. So it's not squared. So what this ends up doing is in the ridge regression, the coefficients can get pretty small, but they can't get to 0. With the lasso regression though, the coefficients can end up being equal to 0. So in a way, lasso regression ends up eliminating some of your features that aren't important. So it kind of performs feature selection, just like we were doing with the recursive feature elimination. So here's some like comparisons between the two. So they both include all the features and they try to shrink the coefficients, but lasso regression can shrink the coefficients to 0, thus performing feature selection. So in general, Ridge is better with less features. Lasso is better with more because Lasso can eliminate the unimportant ones. If you have correlations between features, Ridge is probably going to be better. What it does is it'll split the coefficient between the two. But Lasso will actually, if you have, say, so say x1 and x2 are highly correlated. So Ridge, if it figures out that the correlation should have a coefficient of 5, it would give like 2.5 to both of them. But Lasso, on the other hand, it would choose one at random, say x1, and give that a coefficient of 0, and then give the rest of the coefficient to x2. So if you have a lot of correlation, you probably want to do Ridge instead.
Why wouldn't you always want to use the lasso if it performs feature selection?
Well, basically because of this last part here, how they handle correlation. Because sometimes you don't want it to just be arbitrary, like which one gets set to 0. If there's a correlation, you might want to include both of them instead of dropping one.
Yeah.
But in general, Lasso is the preferred one and probably used most often. All right. So now we're going to start off by building a ridge regression on our data. This is with all of the interactions, so we'll see what it does here. So this gave us a pretty good result, a little bit worse than our RFE method, but still pretty good. And now we can also view the coefficients that it generated. All right, and then we can do the same for Lasso. So about the same, really. And then we can view the parameters here. So for Lasso and Ridge, you can do it either in stats models or sklearn. If you do it in stats models, you have access to AIC, BIC, adjusted R squared, all these metrics like really easily. sklearn doesn't have those, but sklearn is a little bit better with their Ridge and Lasso regression. You can play around with the parameters a little bit better. Basically though, if you're using stats models, let me go back here. You'll notice how I did this here. So this line here. So you have to do fit regularized instead of just fit. This is usually stats models. And then for Ridge, you have to set this parameter here, L1 weight, to 0. And that tells it to be in Ridge mode. And then if you go to the Lasso one, it's basically the same thing, except the L1 weight has to be set to 1. And that will make it a Lasso. So we can print out the params here too. You'll notice that none of them went to 0. This is because, remember that like lambda from the loss function, the parameter, basically in this situation, it's known as alpha, and its default is set to 1, I believe. So if we set it to 1, or no, the default's 0. So the default is to not include that penalty term at all, in which case none of the coefficients get reduced to 0. But if we increase this just slightly, my mouse is like all out of whack here. Let's see. So if we just put like a small value here and then run the coefficients again, we can see that now it dropped some of those because we gave some weight to that penalty term. So it ended up dropping some of these coefficients that aren't important. But you can see the adjusted R squared took a hit and the AIC and BIC changed a little bit. We can increase this even more to like say 0.50. The adjusted R squared went way down, but you can see we eliminated a lot more features. And basically these first 8 features are like x1 through x8. So like we know those are probably important to keep, and a lot of these ones in the middle probably are not important. So that's kind of a thing to keep in mind. You can play around with that alpha value to control how tight of a lasso it basically puts around your coefficients and how many features it ends up dropping. All right, so now our best model ended up being that RFE method with the 19 features. So we're gonna go with that. We're gonna fit a model to it. And then just to compare, this isn't like the normal way you would do things, but just to compare to our train and test mean squared errors we had originally, I'm going to train that 19 feature model on both of those and see what we get for the mean squared errors. So originally, with all the interactions, we had the train mean squared error here of 2 something, the test of 60, we were overfitted. Here we see we closed that gap a bit. Our train went up a little bit, but our test went down a lot. So this is a little bit better, a little less overfitted. But you can see there's still a discrepancy here. We probably still could do more. In this case, we might want to use the lasso method and eliminate more features. Or if we want to stick with the RFE, we might want to just lower that number of features. And we might get train MSE and test MSE closer together here. So basically, that's kind of a walkthrough of how you would go about this. You have a lot of metrics to consider with the adjusted R-squared AIC and BIC, but ultimately you're trying to make your model just complex enough so that it fits to your training data well, but not too complex so that you can't adjust to new data. So with that, we're going to go into an activity. So there's a CSV file called data. It's similar to the data set we were just working with. You're basically going to try and use some of the techniques above. You don't have to do everything. You don't have to just like copy and paste it all and do the exact same stuff. You could just pick 1 or 2 of the methods and try those out. But you're basically trying to fit a model to the data and to try and not have it be overfit. So with that, we'll pause sharing or pause recording.
So we first just import the data and we check the data. There are 8 variables and 1 target. And the first step, we just use sklearn, train test split, and to get train data and test data. So x train, x test, y train, y test. And we choose the test size is 0.25. And later, we just run a OLS on all the data and get the base model. And our train MSE is 16 and test MSE is 25. And then we plot all the variables on a matrix, and we actually didn't find any obvious correlation here. If we look at X1, look at the last row, it seems pretty scattered. So, and then we run a heat map, which shows the correlation. And it seems among the variables, there's no obvious correlation. So we had a feeling that maybe compared to interaction term, polynomial terms are more, make more sense. So we use sklearn preprocessing, import polynomial features, and we tried a different degree. And we tried 2 and 3. And in terms of the train and test MSE, it seems degree equals 3 give us a better MSE. So we decided to go with degree equals 3, which gave us give us a lot of terms. So we have the individual variables, and we have the interactions. We also have quadruple and I mean degree 3. So what was that called?
Cubic.
Cubic. Yeah.
Yep.
Yeah. So we ended up have 165 terms features, and then apparently we're overfitting here. So we run a summary and found that the adjusted R square is none and R square is 1, and yeah, the AIC and BIC, they're all negative, big negative numbers. So the next step,
just to add something there, what happened here is OLS from stats models can only handle so many features. It's one of the flaws of it. So basically here they had too many features. And so you got like not a number for adjusted R squared, and basically everything messed up. So yep.
Right. So then we decided to use sklearn to get the model. So here we import linear regression from sklearn linear model and get all the coefficient. So this model, after that, we did a feature selection. So use the RFE code here and draw the adjusted R square chart with the AIC and BIC chart. One thing we changed here is to set a limit to the x-axis, or it will just show 165 features and we don't know where is the intercept. So it seems like the intercept happened between 48 and 49, and there is a huge jump after 48. So I actually tried 48 and 49, and it all gives me non-R squares. So it probably overfitting. So I chose 47 here. So this is a result of my model with 47 features. And then do a comparison before reduced features. My like before model has a train MSE of 3.9 and test MSE of 56, but after reduced features, I have a better result. So yeah, we would just think this is better.
Yep, it's less overfitted, basically.
Yep.
All right, your turn, Beth.
All right. Yeah, we did something completely different. We approached everything a little bit differently. So here we read in our data frame, we set up our X and our Y, took a peek at the data, and this was our original R squared, our original adjusted R squared. Our AIC and BIC were lower than what we saw in the other activity, not that that means a whole lot. And then we took a look at the shapes of the data as well. So we plotted each feature against the target, and this looks very scattered, and all of these look pretty scattered until we got to here. And this X7 looks like it might have some sort of shape going on, some sort of trend, and so does X8. And to me, that kind of indicates that there's a polynomial present. And so we looked at what those possible polynomials might look like. This is for X8, just arbitrarily picked 10. And we noticed some interesting things about our data. One of the things that we found was if you look at the adjusted R squared value, sometimes the R squared value will do weird things. Like I don't know. Earlier we had a -1 in there somewhere.
Or wait, change that back there. Like add the adjusted on that one
I
that
think
you're
it was
looking at.
11 and X7.
Yeah. So here we saw that our R-squared value actually went negative. So we know for sure that it's not to the 9th degree for our X7. And we theorized that maybe the best way to maybe look at, because all of the MSE graphs, they look pretty similar. They drop and then they go back up and then they start to go back down. That maybe we should be looking at orders where the minimum is equivalent on the other side of this increase, maybe. So because of that, for both of these, we decided to include up to an order of 6 as part of our features. Just for numbers 7 and 8, there's the addition of those features there. Reset up my X variable to include all of these new features. Then here, the same thing that you got, Bonnie, we had originally our adjusted R-squared was not a number. So I dropped the R-squared value just to see what the actual R-squared was. And it looks like we're overfitted at this point in time. And then I ran a feature selection just to see if I could get anything out. And I didn't, because I'm dividing by 0 or something somewhere. I decided to plot what was going on just to see what our adjusted R-squared is doing as we add more features. And the total number of features that we had was less than 20. So we're somewhere in here. And so the same graph that you had earlier, Bonnie. I'm not really sure what's going on. I haven't had time to troubleshoot it yet, but it's there. And then the this is still the same X and Y. There we go. Here's our new R-squared value and our AIC and our BIC. They are lower than they were originally. Our R-squared is higher. So we have 301 and 337 compared to our original model. I guess they're higher, but our R-squared went up. So there's that.
All right, cool. Thank you.
Mm-hmm.
All right, so before we go, does anyone have any questions? I know this was a lot, so feel free to schedule a one-on-one this week. No questions right now?
So Matt, about the holiday challenge, are you going to going through that with us?
Right, so that's my last thing of business tonight. So after speaking to people and also considering the fact that there were no submissions to the holiday challenge problem, I realized that maybe you guys should just have more time for it. With all this new linear regression stuff, I think you might have a better way of attacking it. So I'm just going to extend it like 2 weeks. So it'll stay up there. All the stuff you learned tonight and what you'll learn Wednesday will come in handy. So yeah, so just make sure you start doing submissions here at some point. I don't know if any of you have done a Kaggle competition before, but basically you get 2 submissions a day to test your model against the hidden like test data or validation data. So every day you can upload 2 different models, 2 different sets of predictions to kind of see where you're at. So it's something you kind of want to start doing early before the deadline, so you get lots of trials and you kind of know where you're at before the end. But so yeah, so it's going to get a 2-week extension, so keep working on it.
Okay.
Yep.
Cool. And after the deadline, you'll go through that with us.
Yep, we'll have a whole study group for it probably.
Okay. Cool. Thanks.